Let's jump into the last part of this. This is going to be part 5 of improper integrals, section 7.8. I'm not going to do, so there's a section in here on comparison test. I'm going to skip over that because it's not included in your homework. It's interesting if you want to read it. It's a little, I feel like it might be a little too much analysis. I don't want to get into the weeds with that. So let's do this example. We have 2 examples left in this section. So this first example is we want to integrate we want to evaluate the integral from 0 to 3 dx over x minus 1, if possible. What you should notice here is, 1 over x minus 1 is discontinuous at x equals 1. And x equals 1, falls in this interval between 0 and 3. So, in the previous 2 examples, we saw an example where our function was shooting off to infinity as we approached, the top bound. We saw it was shooting off to infinity as we approached the bottom bound of our integral. And this integral is shoots off to infinity in the middle. So we have to treat that as part C. So I'm gonna just go ahead and, so I'm not gonna jump back yet, but so the way, part C of that definition tells us to handle this is we're gonna write it like this. So the integral from 0 to 3, 1 over x minus 1 dx. So let's just write dx over x minus 1. This is going to be the integral from 0 to 1 dx over x minus 1 plus the integral from 1 to 3 dx over x minus 1. And now we treat these like we would the improper integrals we've seen before. This is the limit as t approaches 1 from the left, integral from 0 to t dx over x minus 1 plus the limit as t approaches 1 from the right, the integral t to 3 dx over x minus 1. Now I'm going to jump back to the definition we used. Is it part 3? Nope, it is part 4. So I just want to flip back over here. So I want to point out that, what this definition says is, we can break up this integral, but one thing we need here is we need that both, so if f has a discontinuity where at c where c is between a and b, and this is true, we need the integral f of x dx from a to c and the integral from c to b f of x dx to be both convergent. So when we do this problem that we're doing now, we can check either one of these, we can check them both, but if we find that one does not converge, then we're finished. The problem can't be done because one of these doesn't converge. It doesn't fit into the definition of our problem. The definition presupposes that, both of these are convergent. So let's look at the limit, go back to marker. The limit t approaches 1 from the left, integral 0 to t dx over x minus 1. Let's see if this converges or not. And if it does, we'll check if the other one converges. And then we can just add those together. This is going to be the limit as t approaches 1 from the left. This integral is one that we know, or should be able to do by now. ln of x minus 1 absolute value from 0 to t, which is the limit t approaches 1 from the left. And then we evaluate ln absolute value of t minus 1 minus ln absolute value of minus 1. So the limit t approaches 1 from the left. ln of minus 1 absolute value is ln of 1, which is 0. So this is just ln of the absolute value of t minus 1. And as this approaches infinity, as t approaches 1 from the left, this ln is approaching 0, ln of the absolute value. It's approaching 0. And if you think about what this does, what ln does as, we approach the x equals 0, the origin, this goes to negative infinity. So because the integral from 0 to 1 dx over x minus 1 is divergent, we cannot evaluate the integral from 0 to 3 dx over x minus 1. And again, this is because in our definition of, this type of integral, we have to have that both of the integrals that we break it up into converge. This one does not converge, so we can't use our definition to do the problem. So I'm going to do the next problem. So one thing I just want to point out is that, if you'd seen a problem like this before we talked about these improper integrals, you would have just integrated and evaluated at 3, evaluated 0, subtracted the 2, and called that your answer. The problem with that is, so to do that, you have to use the fundamental theorem of calculus. The problem there is the fundamental theorem of calculus supposes that the function that you're integrating is continuous on whatever interval you're integrating over. So because, this function isn't continuous on 0 to 3, then I can't use the fundamental theorem of calculus. You have to be careful with that. Always look for discontinuities and then treat it as an improper integral. Again, because, on exam 2, we're not going to point out, this is an improper integral, evaluate it. You're going to have to see that it is an improper integral. So let's do this last example, and then we'll be finished with this section. I'm gonna try and record just a quick review. I'm not gonna do a ton of problems, but just give the highlights of each section, the important information. I'll do a review. I'm gonna try and record it on Monday. This has been a busy semester for me, so I'm behind on a lot of stuff. I wanna get your guys' your quizzes graded as quickly as possible too. So let's just go ahead and jump in. We're gonna do example 8. We have the integral from 0 to 1, ln of x dx. And this is improper, type 2, because the limit as x approaches 0, ln of x is negative infinity. So this thing is, approaching, has a vertical asymptote at 0. So we'll treat this the way we know how to. So this is the integral from 0 to 1 ln of x. Its discontinuity is at 0, so we're going to do the limit as t approaches 0 from the right, integral from t to 1 ln of x dx. Now this is one of those integrals that we actually have to think about how to do. This is going to be an integration by parts. So for this integration by parts, the only choices you have are u is equal to ln of x and dv is equal to dx. Otherwise, you can't. You're just going to pick dv to be ln of x, which is the integral we're trying to find anyway, so that doesn't do anything for us. du is 1 over x dx, v is x. So this thing is going to be equal to the limit t approaches 0 from the right, the integral from t to 1, and get rid of that. We're doing integration by parts here. And then, so that integral is going to turn into uv, so x ln of x, minus the integral v du. So v is x, so I get x du, 1 over x dx. And we're going to evaluate this from t to 1, and this is the integral from t to 1. And we just continue. So this is the limit as t approaches 0 from the right. So we're going to get, when we plug in 1, we're going to get ln of 1 minus t ln of t. And then this integral here, so this integrand is just 1. So I'm integrating dx, so that integral is just x, evaluated from t to 1. So this is the limit t approaches 0 from the right. Ln of 1 is 0, so I'm going to get minus t ln of t, and then minus, and when I plug these in, I'm going to get 1 minus t. T approaches 0 from the right, negative t ln of t minus 1 plus t. And again, if I look at this, this is like that one of the earlier problems we did where we had to use L'Hopital's. I ended up with 3 terms. 2 of them I can take the limit of. The first one here I can't because it's not in the right form. So we're going to try and figure out what the limit t approaches 0 from the right, t ln of t is. The other 2 I know. First one's -1, second one's 0. So this -1, its limit is -1. T as t approaches 0 from the right is 0. So this is going to be a L'Hopital's problem. Right now, it is in the form 0 times minus infinity, indeterminate. So notice I'm not writing equals. I'm saying it's, it's going to, or I'm indicating that it's 0 times negative infinity, indeterminate. So I need to rewrite this. So remember, to do this, if I have an indeterminate form of 0 times infinity, I just make 1 the reciprocal. And the easiest thing to do is to leave the ln alone. Otherwise, you're going to have to really take the derivative of something gross and then divide by the reciprocal of t. So divide by 1 over t. And now we can see that this is an infinity over infinity indeterminate. It says ln approaches, as t approaches 0, ln of t approaches negative infinity. As t approaches 0, 1 over t approaches infinity. You can stick a minus sign in there if you want, it doesn't matter. We're allowed to use L'Hopital's is the point here. So this is the limit as t approaches 0 from the right. Derivative of ln of t is 1 over t. Derivative of the bottom is -1 over t squared. This is the limit t approaches 0 from the right, and I just simplify. I get -t. And this limit is 0 in this case. So now I can put all of this together. So I'm going to come back up here, and I have the limit as t approaches 0 from the right of t, -t, ln of t, -1 plus t. First one we just found to be 0. Second one is 1. Last one is 0. This is -1. I think it was -1 on the other example we did like this. But yeah, so that's what we've been doing is pretty repetitious. We have to bring back our ideas of limits. But the good news is we've learned L'Hopital's. That makes it easy to evaluate some of these harder limits. Yeah, so I'm going to stop here. If you have questions about this section, feel free to email me. Leave a comment on the video. I don't think there are going to be many mistakes in this video. I'm trying to do a better job of checking myself as I go. Sometimes I'll skip checking myself because I think it's an easy bit of math, and that's when I mess up. But yeah, so if you notice something off, let me know. I'll address it, but I'll stop the video here.